Hello and welcome, fellow traveler. Tonight, we're going on a very particular kind of journey. Not just learning about something from a distance, but actually experiencing it step by step, in the safest way possible, through imagination and science. We're going to answer a question that's fascinated people for decades. What would actually happen if you fell into a black hole? Not the movie's version, with action and dramatic music. The real thing. What would you see? What would you feel? What would the experience actually be like, according to our best understanding of physics? Before we begin, get comfortable. Really comfortable. This is going to be a long, slow journey, and there's no rush at all. Adjust your position, let your breathing settle into a natural rhythm, and allow the concerns of the day to fade into the background. If you enjoy these journeys through the cosmos, you're welcome to subscribe. We create these peaceful explorations regularly, and you're always invited to join. But for now, just be here. Just listen and relax. Let yourself drift along with the story. Now, I want to be clear about something from the start. This journey is based on real physics, real science, but it's also completely safe. You're here, comfortable, on Earth. The nearest black hole is thousands of light years away. We're simply using our imagination, guided by mathematics and observation, to explore what would happen. And here's something important to understand. Falling into a black hole wouldn't necessarily be the terrifying experience you might imagine. In fact, if you chose the right black hole, parts of the experience would be surprisingly peaceful. Strange, yes. Disorienting, absolutely. But not immediately violent. The key is choosing a supermassive black hole rather than a small one. We'll explain why as we go. So let's begin. Let's imagine you're an astronaut in the far future, and you've volunteered for the most extraordinary mission in human history, to journey to a black hole and across the event horizon, sending back information as long as possible about what you experience. You're brave, and you're very, very far away from home. Let's walk through what happens step by step. Moment by moment, your spacecraft approaches the black hole from a great distance. At first, you can't see it. Black holes don't emit light, so there's nothing to see directly. But you know it's there because of everything around it. Your destination is a supermassive black hole, one with about 10 million times the mass of our Sun. This is similar to the black holes found at the centers of many galaxies. Though you've traveled to one in a relatively isolated region of space, far from the bright accretion disks and dangerous radiation that surround the ones in galactic centers. Why a supermassive black hole? Because the tidal forces at the event horizon are much weaker for larger black holes. A stellar mass black hole, one formed from a collapsed star, would tear you apart long before you reach the point of no return. But a supermassive black hole's event horizon is so large that you can actually cross it intact. The event horizon of your destination is about 30 million kilometers in radius. For perspective, that's about the distance from the Sun to Mercury. It's enormous. As you get closer, you start to see the first effects. Behind the black hole, there are stars. Lots of them. And as you watch, their positions seem wrong. They're displaced from where they should be, distorted, stretched into arcs. This is gravitational lensing. The black hole's gravity is so strong that it bends the path of light passing near it. Light from stars behind the black hole curves around it, creating distorted, magnified images. As you change your position, these lensed images shift and dance. Stars seem to slide around the black hole's position in ways that defy normal perspective. It's beautiful. In a disorienting way, the sky itself is being warped by gravity. You also notice something else. The region where the black hole seems darker than the surrounding space. Not pitch black yet, but darker, like a circular shadow against the star field. This is the black hole's shadow, slightly larger than the event horizon itself. It's the region where light rays are bent so strongly that they either fall into the black hole or curve away from your line of sight. No light from behind the black hole can reach you from that direction. The shadow has a strange quality to it. Its edge is perfectly sharp, perfectly circular, as if someone cut a hole. In reality, you're still far away, still safe, but you can feel your heartbeat quickening slightly. This is real. You're actually here, approaching an object so extreme that the rules of reality itself bend around it. Your spacecraft has no windows, not in the traditional sense. The radiation environment near black holes can be hazardous, so you observe everything through cameras and sensors that feed information to screens around you. But for our purposes, let's imagine you can see directly, that you have perfect protection and perfect vision. As you get closer, the gravitational lensing effects become more pronounced. The stars behind the black hole aren't just displaced now. They're smeared into a ring, a circle of light surrounding the black hole's shadow. This ring is called the photon ring, and it's made up of light that's been bent almost into a complete circle around the black hole before escaping toward you. If you had impossibly perfect vision, you'd see that this ring actually contains multiple nested images. Light that's orbited the black hole one time, 2 times, 3 times before reaching you, each successive ring fainter and thinner. But even without that level of detail, the sight is extraordinary. A perfect circle of starlight surrounding a darker-than-night shadow with distorted star fields all around. You notice something else peculiar. The distribution of light around the shadow isn't even. One side of the ring is brighter than the other. This is because the black hole is rotating, spinning like a vast cosmic top. And on the side where the rotation carries matter toward you, the light is blue shifted, compressed to shorter wavelengths and appearing brighter. On the side rotating away, the light is red shifted and dimmer. You're seeing the effects of relativistic beaming. Light from matter moving at a significant fraction of the speed of light. Your instruments confirm what you already know. There's no going back after this. Your spacecraft has already crossed what's called the innermost stable circular orbit. You could still escape with your engines, but the mission is to go forward, to cross the horizon, to see what lies beyond. You take a deep breath. You send a final message back to whoever might be listening, light years away. The transmission will take years to reach anyone, and by the time it does, you'll have long since crossed the event horizon. Then you orient your spacecraft, feet first, toward the black hole and begin the final descent. As you fall closer, you start to notice something strange about your own body. There's a sensation, subtle at first, like being stretched very gently. Your feet feel slightly heavier than they should, as if there's a gentle pull on them. Your head feels slightly lighter. These are tidal forces, and they're beginning to become noticeable. Here's what's happening. Your feet are closer to the black hole than your head. Not by much, you're about 2 meters tall, but that 2-meter difference matters. Gravity follows an inverse square law. Double your distance from a massive object, and the gravitational pull becomes 1/4 as strong. Halve your distance, and it becomes 4 times as strong. Your feet, being closer to the black hole, experience slightly stronger gravity than your head. This creates a stretching sensation along your body dot at the same time. Your left side and your right side are both being pulled toward the center, toward the point where the black hole is. This creates a gentle compression from the sides. Stretch lengthwise, squeeze from the sides. The sensations are still mild, uncomfortable, perhaps like wearing a suit that's slightly too tight in some places and pulling at you in others, but not painful. Not yet. This is one of the key differences between a supermassive black hole and a stellar mass one. For a small black hole, these tidal forces would already be tearing you apart. But you're still far from the event horizon of this massive black hole, and the tidal forces here are surprisingly gentle. You check your instruments. Your local clock is ticking normally from your perspective, 1 second per second, just as it always has. But your instruments also show you something else. They're tracking the time signals from the distant universe, from the spacecraft and stations you left behind. And those signals are arriving faster than they should. Time in the outside universe appears, from your perspective, to be speeding up. Every minute that passes for you, more than a minute passes out there. The difference is small so far, but it's measurable and growing. This is gravitational time dilation, one of the strangest predictions of Einstein's general relativity. Time doesn't flow at the same rate everywhere. It flows slower in stronger gravitational fields. You're deep in the black hole's gravitational well now, so time for you is flowing more slowly compared to the distant universe. From your perspective, the universe outside is speeding up. From the perspective of observers far away, you're slowing down. Both perspectives are equally valid. They're just different views of the same reality. You continue falling, and the black hole's shadow grows larger in your view, eventually filling half your field of vision. Then more. The distortions in the star field become more extreme. Stars that should be behind you, back in the direction you came from, appear to slide around toward the edges of your view. The light from them is being bent so severely by the black hole's gravity that you can see light from almost every direction converging into a ring around the edge of the black hole's shadow dot. It's as if the entire universe is being compressed into a narrowing circle behind you. While the darkness ahead expands, you also notice colors shifting. Light from the stars ahead in the direction you're falling is becoming bluer, shifting toward shorter wavelengths. Light from behind is becoming redder, shifting toward longer wavelengths. This is the Doppler effect, combined with gravitational effects. You're falling faster now, a significant fraction of the speed of light, and light is being compressed ahead of you and stretched behind you. The tidal forces are stronger now. The stretching sensation has gone from uncomfortable to painful. It feels like someone is gently pulling your feet away from your body while pushing on your shoulders, all while squeezing your sides. Your onboard medical systems administer medication to manage the pain, though they warn you that the forces will continue to increase. You look at the measurements. You're approaching the event horizon. In your own reference frame, you'll cross it in about 15 minutes. 15 minutes until the point of no return. You check the signals from the outside universe again. The time dilation has become more extreme. For every minute that passes for you, hours are passing out there. The universe is fast-forwarding from your perspective. If you could somehow maintain a video link to the outside world, which you can't because of the extreme light bending and redshifting, you'd see civilization rising and falling in fast forward. Stars being born and dying, galaxies evolving, but you can't see that. The light from the outside universe, as you get closer to the event horizon, becomes increasingly redshifted, stretched to longer and longer wavelengths, carrying less and less energy. From your perspective, the universe behind you is gradually fading to darkness. Its light stretched almost into invisibility. From the perspective of anyone watching from far away, something different is happening. Let's pause your journey for a moment and shift perspective. Imagine there's an observer far from the black hole, watching you with an impossibly powerful telescope. Let's call them the outside observer. From their perspective, as you fall closer to the event horizon, you appear to slow down. It's not an optical illusion or a trick of measurement. From their reference frame, you are actually slowing down. Your spacecraft's engines glow as you fire them for some last-minute adjustment. But the light from those engines is red-shifted, stretched to longer wavelengths, appearing redder and dimmer than it should. You appear to be moving in slow motion. As you get closer and closer to the event horizon, from the outside observer's perspective, you slow down more and more, asymptotically approaching, but never quite reaching the horizon. The light from you becomes increasingly red-shifted and dimmed. First you appear red, then infrared, then your image fades into the radio spectrum, becoming dimmer and dimmer. From the outside observer's perspective, it takes infinite time for you to reach the event horizon. You appear to freeze there, your image fading away, becoming darker and redder, eventually disappearing from view entirely, but technically never crossing. This seems like a contradiction. How can you cross the horizon in 15 minutes by your clock, while from the outside perspective it takes forever? The resolution is that time is relative. Different observers in different reference frames experience time differently, especially in strong gravitational fields. Both perspectives are valid. Both are describing the same physical reality from different viewpoints. From your perspective, you cross in finite time. From the outside perspective, you never quite cross, but your image fades away into invisibility. There's no contradiction, just a strange reality of how time works in curved space-time. But let's return to your perspective, because that's the journey we're on. You're minutes away from the event horizon now. The tidal forces have become severe. Your medical systems are working hard to keep you conscious, managing pain, supporting your cardiovascular system against the stretching and compression. It feels like being on a rack, gently but inexorably pulled longer and thinner. Every bone aches. Your spine feels like it's being stretched. The pressure on your sides is constant and growing, but you're still intact, still conscious, still gathering data. The black hole's shadow fills almost your entire forward view now. The ring of light from the compressed universe behind you has narrowed to a bright band around the edge of your vision. And then, without any fanfare, without any dramatic change, you cross the event horizon. For a moment, you're not sure it's happened. Your instruments confirm it, marking the moment in your records, but physically, you feel no discontinuity. There's no membrane to pass through, no barrier, no sudden change. The tidal forces continue exactly as they were. The view continues to evolve smoothly. Your clock continues ticking, but something fundamental has changed. Behind you, the direction back toward the outside universe has stopped being a possible future direction. You could fire your engines in that direction. You could accelerate with all the power available to you, but you wouldn't move away from the center. You'd only slow your fall inward. Every possible future path you could take now leads deeper into the black hole, toward the singularity at the center dot. This is what the event horizon means. It's not a physical barrier. It's a point of no return in the structure of space-time itself. The direction toward the singularity, which was a direction in space when you were outside, has become a direction in time now that you're inside. Moving toward the singularity has become as inevitable as moving. Forward in time, you can no more avoid falling toward the center than you can avoid your next birthday dot inside the event horizon. The nature of space and time has fundamentally changed. Outside, the black hole's pull was a force you could resist with your engines, at least in principle. Inside, it's not a force anymore. It's the structure of time itself. The singularity at the center is in your future. As inevitable as tomorrow, you check your instruments to see how much time remains. The calculations are complicated because space-time itself is so warped here. But the estimate is about 40 minutes of your subjective time before you reach the singularity. 40 minutes left. The tidal forces are growing stronger minute by minute. The stretching sensation has become extreme. Your spacecraft's structural integrity is being tested. Metal and composite materials groaning under forces they were never designed to handle. The view has changed too. The bright ring of light from the outside universe has shifted strangely. It's no longer behind you. In fact, the concepts of behind and ahead are becoming confused. Light from the outside universe can still reach you, even though you're inside the event horizon. That light fell in after you did, and it's still propagating through this region of space-time, but the directions are strange. The light seems to come from all around you, a dimming glow that surrounds you in every direction except toward the singularity. Ahead of you, toward the center, there's only darkness. Not the darkness of empty space, but a deeper darkness, an absence of light so complete it's like looking at the end of everything. And in a sense, that's exactly what it is. The singularity is where space-time itself ends, where the curvature becomes infinite, where all known physics breaks down. You're falling toward the edge of the known universe, toward a place where the laws of nature, as we understand them, cease to apply. The pain has become intense now. The tidal forces are pulling at you with tremendous strength, stretching you, compressing you. Your spacecraft begins to break apart. Metal screams. Bulkheads rupture. Systems fail one by one. You're in a protective suit, designed to keep you alive as long as physically possible, to gather data until the very end. But even the suit can only do so much. Your bones are being stretched. The difference in gravitational pull from your feet to your head is now thousands of times your body weight. Your spine elongates. Your legs stretch longer and thinner at the same time. You're being compressed from the sides. Your ribs ache under the pressure. Your shoulders are pushed inward. This is spaghettification in earnest now. The technical term is tidal disruption, but spaghettification captures the essence, being stretched into a long, thin strand. Remarkably, you're still conscious. Though the medical systems in your suit are delivering massive doses of medication, blocking pain signals, supporting vital functions, you're still transmitting data, though there's no one who will ever receive it. The signals you're sending can't escape the event horizon. They're falling toward the singularity just like you are. But the mission was never to send data back. It was to record it, to preserve it, to see how far you could go. And you're still going as the minutes pass. The tidal forces reach levels that no material can withstand. Your suit ruptures. The protection fails. Your body begins to come apart. Let's be clear about what this means without being graphic. The tissues of your body can only handle so much stress. When the difference in gravitational pull from one end of a cell to the other becomes too large, the cell membrane ruptures. This happens to every cell in your body almost simultaneously, starting from the extremities where the tidal forces are strongest. Your physical form essentially dissolves into a stream of particles, still falling toward the singularity, but no longer organized into anything resembling a human body. Consciousness ends. There's no pain in this final moment, because the structures that process pain are among the first to fail. But the atoms that were you continue falling. And here's something profound to consider. Those atoms that matter carries information. Every particle has properties: mass, charge, spin, quantum state. What happens to that information? According to classical general relativity, it all falls into the singularity and is lost forever, crushed out of existence at the point of infinite density. But according to quantum mechanics, information can't be destroyed. It has to be preserved somewhere, somehow. This contradiction is the heart of the black hole information paradox, one of the deepest unsolved problems in theoretical physics. Does the information get encoded in the structure of space-time somehow? Is it preserved in the event horizon itself? Does it radiate back out through Hawking radiation over the eons as the black hole eventually evaporates? We don't know. It's a question that touches on the fundamental nature of reality, on how quantum mechanics and gravity work together at the deepest levels. But for the atoms that were you, falling through these final moments, the immediate fate is the singularity. What is the singularity? Mathematically, it's a point where the curvature of space-time becomes infinite. Density becomes infinite. The equations of general relativity produce infinities, which is usually a sign that the theory has broken down, that it's being pushed beyond its domain of validity. Most physicists believe that before you actually reach a mathematical singularity, quantum effects become important. At the incredibly small scales and incredibly high energies near the singularity, we'd need a theory of quantum gravity to describe what happens. We don't have such a theory yet. String theory, loop quantum gravity, and other approaches offer possibilities, but none are confirmed or complete. So we can't say with certainty what happens at the very center of a black hole. Maybe space-time forms some kind of quantum foam, a seething microscopic structure where the smooth fabric of space-time breaks down into discrete units. Maybe there's a bounce where the collapse reverses and matter emerges elsewhere, perhaps into another universe or another region of space-time. Maybe there's something we haven't imagined yet, something that requires entirely new physics to understand. The singularity is hidden behind the event horizon, forever cut off from the outside universe. We call this cosmic censorship, the idea that nature hides singularities behind event horizons, so we never have to directly confront them. It's as if the universe is protecting itself from its own infinities, keeping them veiled where they can't cause problems for the smooth functioning of physics elsewhere. Let's step back now and think about what we've just experienced, because the journey into a black hole, as strange as it is, tells us profound things about the nature of reality. First, time is not absolute. It flows at different rates in different places, depending on gravity and velocity. This isn't philosophy or speculation. It's measured fact, confirmed by countless experiments. Near a black hole, this effect becomes extreme enough that observers in different locations can disagree profoundly about when events happen, about how long things take, even about what's possible. Second, space and time are not separate things. They're woven together into a unified fabric that can be stretched, compressed, and warped by mass and energy. The event horizon is a place where this warping becomes so extreme that space and time exchange roles. The direction toward the singularity, which was a direction in space outside, becomes a direction in time inside. This isn't a metaphor. It's a literal consequence of how the geometry of space-time works in Einstein's general relativity. Third, gravity isn't really a force in the Newtonian sense. It's the curvature of space-time. Objects in free fall aren't being pulled by some mysterious force. They're following the straightest possible paths through curved spacet IMA.u. Falling into the black hole where in free fall, you felt weightless the whole way down, except for the tidal forces, which are a different effect. The black hole wasn't pulling you. You were simply following the geometry of space-time to its inevitable conclusion. Now, let's consider what would have been different if you'd chosen a different black hole. If you'd approached a stellar mass black hole instead of a supermassive one with perhaps 10 times the sun's mass instead of 10 million times, the experience would have been much shorter and much more violent. The event horizon would be only about 30 kilometers in radius instead of 30 million kilometers. The tidal forces at the event horizon would be about 1 million times stronger. You'd be torn apart long before you reach the point of no return. Your spacecraft would be shredded. Your body would be disrupted into individual atoms. While still far outside the event horizon. There would be no gentle crossing, no minutes or hours to contemplate the experience, just rapid, violent destruction. This is why we chose a supermassive black hole for our journey. It's the only type where you could conceivably cross the event horizon while still intact and conscious. The irony is beautiful in a way. The most massive, most powerful black holes are actually the gentlest at their event horizons. The larger the black hole, the weaker the tidal forces at the boundary of no return. A black hole with 1 billion solar masses would be even gentler at its event horizon than the one we visited. You could cross it without even feeling significant tidal forces initially. Of course, you'd still be torn apart eventually as you fell toward the singularity. The singularity is always deadly, regardless of the black hole's size. But at least you'd make it past the event horizon first. What if the black hole were rotating? We assumed a non-rotating black hole for simplicity, but most real black holes probably rotate. They form from collapsing stars or from merging black holes, and these objects almost always have some angular momentum. A rotating black hole is described by a different solution to Einstein's equations. Discovered by Roy Kerr in 1963, it's called the Kerr metric, and it's significantly more complicated than the Schwarzschild metric for non-rotating black holes. Rotating black holes have some fascinating additional features. First, they drag space-time around with them as they rotate. This is called frame dragging. Close to a rotating black hole, space-time itself is rotating, and anything in that region is forced to rotate with it. At least to some degree, you can't stand still near a rotating black hole, not in any absolute sense. Space-time itself is moving, and you move with it. Second, rotating black holes have two event horizons instead of one, an outer event horizon and an inner event horizon. Between them is a region called the ERGOSPHERE dot in the ergosphere. You can still escape back to the outside universe, but you can't remain stationary. You're forced to rotate around the black hole by the dragging of SPACETIME.3. There's a theoretical possibility of extracting energy from a rotating black hole through a process called the Penrose process. By carefully arranging trajectories in the ergosphere, you could in principle extract some of the black hole's rotational energy. You're still transmitting data, though there's no one who will ever receive it. The signals you're sending can't escape the event horizon. They're falling toward the singularity just like you are. But the mission was never to send data back. It was to record it, to preserve it, to see how far you could go. And you're still going. As the minutes pass, the tidal forces reach levels that no material can withstand. Your suit ruptures. The protection fails. Your body begins to come apart. Let's be clear about what this means without being graphic. The tissues of your body can only handle so much stress. When the difference in gravitational pull from one end of a cell to the other becomes too large, the cell membrane ruptures. This happens to every cell in your body almost simultaneously, starting from the extremities where the tidal forces are strongest. Your physical form essentially dissolves into a stream of particles, still falling toward the singularity, but no longer organized into anything resembling a human body. Consciousness ends. There's no pain in this final moment, because the structures that process pain are among the first to fail. But the atoms that where you continue falling, and here's something profound to consider. Those atoms that matter carries information. Every particle has properties: mass, charge, spin, quantum state. What happens to that information? According to classical general relativity, it all falls into the singularity and is lost forever, crushed out of existence at the point of infinite density. But according to quantum mechanics, information can't be destroyed. It has to be preserved somewhere, somehow. This contradiction is the heart of the black hole information paradox, one of the deepest unsolved problems in theoretical physics. Does the information get encoded in the structure of space-time somehow? Is it preserved in the event horizon itself? Does it radiate back out through Hawking radiation over the eons as the black hole eventually evaporates? We don't know. It's a question that touches on the fundamental nature of reality, on how quantum mechanics and gravity work together at the deepest levels. But for the atoms that were you, falling through these final moments, the immediate fate is the singularity. What is the singularity? Mathematically, it's a point where the curvature of space-time becomes infinite. Density becomes infinite. The equations of general relativity produce infinities, which is usually a sign that the theory has broken down, that it's being pushed beyond its domain of validity. Most physicists believe that before you actually reach a mathematical singularity, quantum effects become important. At the incredibly small scales and incredibly high energies near the singularity, we'd need a theory of quantum gravity to describe what happens. We don't have such a theory yet. String theory, loop quantum gravity, and other approaches offer possibilities, but none are confirmed or complete. So we can't say with certainty what happens at the very center of a black hole. Maybe space-time forms some kind of quantum foam, a seething microscopic structure where the smooth fabric of space-time breaks down into discrete units. Maybe there's a bounce, where the collapse reverses and matter emerges elsewhere, perhaps into another universe or another region of space-time. Maybe there's something we haven't imagined yet, something that requires entirely new physics to understand. The singularity is hidden behind the event horizon, forever cut off from the outside universe. We call this cosmic censorship, the idea that nature hides singularities behind event horizons, so we never have to directly confront them. It's as if the universe is protecting itself from its own infinities, keeping them veiled where they can't cause problems for the smooth functioning of physics. Elsewhere, let's step back now and think about what we've just experienced, because the journey into a black hole, as strange as it is, tells us profound things about the nature of reality. First, time is not absolute. It flows at different rates in different places, depending on gravity and velocity. This isn't philosophy or speculation. It's measured fact, confirmed by countless experiments. Near a black hole, this effect becomes extreme enough that observers in different locations can disagree profoundly about when events happen, about how long things take, even about what's possible. Second, space and time are not separate things. They're woven together into a unified fabric that can be stretched, compressed, and warped by mass and energy. The event horizon is a place where this warping becomes so extreme that space and time exchange roles. The direction toward the singularity, which was a direction in space outside, becomes a direction in time inside. This isn't a metaphor. It's a literal consequence of how the geometry of spacetime works in Einstein's general relativity. Third, gravity isn't really a force in the Newtonian sense. It's the curvature of spacetime. Objects in free fall aren't being pulled by some mysterious force. They're following the straightest possible paths through curved space time. Falling into the black hole or in free fall, you felt weightless the whole way down, except for the tidal forces, which are a different effect. The black hole wasn't pulling you. You were simply following the geometry of space-time to its inevitable conclusion. Now, let's consider what would have been different if you'd chosen a different black hole, if you'd approached a stellar-mass black hole instead of a supermassive one with perhaps 10 times the sun's mass instead of 10 million times. The experience would have been much shorter and much more violent. The event horizon would be only about 30 kilometers in radius instead of 30 million kilometers. The tidal forces at the event horizon would be about 1 million times stronger. You'd be torn apart long before you reach the point of no return. Your spacecraft would be shredded. Your body would be disrupted into individual atoms. While still far outside the event horizon dot, there would be no gentle crossing, no minutes or hours to contemplate the experience, just rapid, violent destruction. This is why we chose a supermassive black hole for our journey. It's the only type where you could conceivably cross the event horizon while still intact and conscious. The irony is beautiful in a way. The most massive, most powerful black holes are actually the gentlest at their event horizons. The larger the black hole, the weaker the tidal forces at the boundary of no return. A black hole with 1 billion solar masses would be even gentler at its event horizon than the one we visited. You could cross it without even feeling significant tidal forces initially. Of course, you'd still be torn apart eventually as you fell toward the singularity. The singularity is always deadly, regardless of the black hole's size, but at least you'd make it past the event horizon first dot. What if the black hole were rotating? We assumed a non-rotating black hole for simplicity, but most real black holes probably rotate. They form from collapsing stars or from merging black holes, and these objects almost always have some angular momentum. A rotating black hole is described by a different solution to Einstein's equations. Discovered by Roy Kerr in 1963, it's called the Kerr metric, and it's significantly more complicated than the Schwarzschild metric for non-rotating black holes. Rotating black holes have some fascinating additional features. First, they drag space-time around with them as they rotate. This is called frame dragging. Close to a rotating black hole, space-time itself is rotating, and anything in that region is forced to rotate with it. At least to some degree, you can't stand still near a rotating black hole, not in any absolute sense. Space-time itself is moving and you move with it. Second, rotating black holes have 2 event horizons instead of 1, an outer event horizon and an inner event horizon. Between them is a region called the ERGOSPHERE dot in the ergosphere. You can still escape back to the outside universe, but you can't remain stationary. You're forced to rotate around the black hole by the dragging of SPACETIMI.3. There's a theoretical possibility of extracting energy from a rotating black hole through a process called the Penrose process. By carefully arranging trajectories in the ergosphere, you could in principle extract some of the black hole's rotational energy. This is purely theoretical and would be extraordinarily difficult in practice, but it's allowed by the laws of physics. Fourth, the singularity in a rotating black hole isn't a point. According to the mathematics, it's a ring, and there are theoretical pathways, at least in the equations, that pass through the ring without encountering infinite curvature. Where those pathways lead is unclear. Some solutions to the equations suggest they might lead to other universes or other regions of space-time, but these solutions probably aren't physically realistic. They involve regions of negative energy density and other exotic features that likely don't exist in nature. Still, rotating black holes add additional layers of strangeness to an already strange phenomenon. Let's talk about what would be different if you weren't alone. If you had a companion watching from a safe distance. Imagine you have a friend in a spacecraft that's hovering far from the black hole, staying in a stable orbit, watching your descent. You've arranged to stay in communication as long as possible. You're both transmitting continuously. From your perspective, falling inward, you receive your friend's signals at an ever-increasing rate. Their voice sounds sped up like someone fast-forwarding through a recording. Their clock appears to tick faster and faster compared to yours. This is time dilation from your perspective. Your friend, being farther from the black hole, experiences time flowing faster than you do. Meanwhile, from your friend's perspective, something very different is happening. They receive your signals at a decreasing rate. Your voice sounds slowed down, deepening in pitch. Your clock appears to tick more and more slowly. As you approach the event horizon, from their perspective, your signals become increasingly red-shifted. The radio waves carrying your voice are stretched to longer and longer wavelengths. Your last signal, transmitted just as you cross the event horizon, is stretched to infinite wavelength. It becomes, from your friend's perspective, infinitely red-shifted. They never receive it. From their perspective, they never see you cross the horizon. Your image appears to freeze just outside the horizon, growing dimmer and redder, eventually fading from view entirely. But you've already crossed from your own perspective. You've crossed and continued falling and reached the singularity, all while your friend is still seeing your frozen image hovering just outside the horizon. Again, both perspectives are valid. Time is relative. Different observers experience the sequence of events differently. This is one of the most profound insights of relativity. There's no absolute universal now that everyone agrees on. Different observers can disagree about the order of events, about how much time has passed, even about what's happening. Reality is more flexible, more observer-dependent than our everyday intuition suggests. Now let's consider an even stranger scenario. What if you could somehow survive the tidal forces? What if you had a body made of some material that couldn't be torn apart, or a consciousness that could exist as a pattern in something other than fragile biological tissue? What would you see in those final moments before the singularity? The mathematics suggests something extraordinary. Light from the outside universe can continue to reach you even as you fall toward the singularity. That light is falling in behind you, and it's blue shifted, compressed to shorter wavelengths and higher energies. From your perspective, as you approach the singularity, you might see the entire future history of the outside universe play out in accelerated fashion. Stars being born and dying, galaxies evolving, the universe expanding and cooling. If you could survive long enough, you might see billions of years of cosmic history compressed into your final moments. Of course, this is highly speculative. The extreme blue shifting would mean this light carries enormous energy, enough to disintegrate anything in its path. And we're assuming you could survive the tidal forces. and the approach to the singularity, which is almost certainly impossible, but it's an intriguing thought. Your final moments could be illuminated by all the light that will ever fall into the black hole. The entire future of that region of the universe, compressed into an instant. Some physicists have speculated about what might be visible if you looked in different directions as you fell. Ahead, toward the singularity, only darkness. No light can come from there. To the sides, complex patterns of distorted light, showing you images of the outside universe from impossible angles, bent and folded by the extreme curvature of space-time. Behind you, the shrinking window to the outside universe, showing you the future unfold at an ever-accelerating rate. It would be the most extraordinary view imaginable. If only you could survive to see it. Let's shift perspective again and think about what happens to the black hole itself during your fall. When you cross the event horizon, you add your mass to the black hole's total mass. The event horizon grows slightly to accommodate the additional mass energy. For a supermassive black hole, your addition is infinitesimally small. Adding a human body or even a spacecraft to a 10 million solar mass black hole is like adding a single drop of water to an ocean. The change in the event horizon's radius is far too small to measure, but the change does happen. The black hole grows. Its event horizon expands. And here's something fascinating. The event horizon expands before you reach it, from the perspective of outside observers. This seems paradoxical. How can the black hole grow from your mass before you've fallen in? The resolution involves the complicated nature of time and causality near event horizons. The event horizon is a null surface, a boundary in space-time defined by the paths of light rays. Its position depends on the entire future history of the black hole, not just the past. So, in a sense, the event horizon knows you're coming and expands in anticipation. This is one of many ways that black holes challenge our intuitive understanding of cause and effect. What about Hawking radiation? Does it affect your journey? Stephen Hawking's theoretical prediction suggests that black holes emit faint radiation due to quantum effects near the event horizon. The basic idea, simplified, is that particle-antiparticle pairs can appear briefly near the horizon. If one falls in while the other escapes, it looks from the outside like the black hole emitted a particle. This process very slowly drains mass energy from the black hole. Over immense timescales much longer than the current age of the universe, a black hole could completely evaporate through this process. But for your journey, Hawking radiation is completely negligible. The temperature of Hawking radiation is inversely proportional to the black hole's mass. For a supermassive black hole, the temperature is incredibly low, far colder than the cosmic microwave background that fills all of space. The black hole is actually absorbing more radiation from its surroundings than it emits through Hawking radiation. You wouldn't detect any Hawking radiation during your fall. Its effects are far too subtle. Even for a stellar mass black hole, the temperature would only be about 1/millionth of a degree above absolute zero, utterly undetectable against the background radiation of the universe. Only for extremely small black holes, if they exist, would Hawking radiation become significant. A black hole with the mass of a mountain might have a temperature high enough to glow detectably. One with the mass of a large building might explode in a burst of radiation as it evaporated completely, but we've never observed such small black holes, and we're not sure they can form naturally. There's a question that often comes up. Could anything ever escape from inside a black hole? According to our current understanding of general relativity, the answer is no. The event horizon is a true point of no return. Once you're inside, every possible future path leads to the singularity. There's no clever trajectory, no amount of thrust, no conceivable technology that could take you back across the event horizon from the inside. Some science fiction stories propose using wormholes to escape, but wormholes, even if they exist, couldn't help you here. You can't create a wormhole once you're inside an event horizon. The singularity is in your future, and nothing can prevent you from reaching it. However, there are some theoretical speculations, highly speculative and not confirmed, about information escaping through Hawking radiation. If Hawking radiation is real, and if it somehow encodes information about what fell into the black hole, then, in a sense, information about you might eventually escape, carried out bit by bit over the eons as the black hole slowly evaporates. But this wouldn't be you escaping. It would be information about you, scrambled and encoded in subtle correlations in the radiation, emerging over timescales longer than the age of the universe. From any practical standpoint, what falls into a black hole is lost forever. Let's talk about the information paradox in more detail, because it's one of the most profound puzzles in theoretical physics. Quantum mechanics has a fundamental principle: information is conserved. The quantum state of a system, which encodes all possible information about it, evolves according to deterministic rules. Information can be scrambled, spread out, transformed, but never truly destroyed. But black holes seem to destroy information. Anything that falls in is crushed at the singularity and lost forever, at least according to classical general relativity. Even if Hawking radiation is real, it was originally thought to be purely thermal radiation with no structure, carrying no information about what fell in. This creates a paradox. Quantum mechanics says information is conserved. General relativity says it's destroyed in black holes. Both theories can't be completely right. Stephen Hawking, who discovered this paradox, initially believed that information was truly lost in black holes, that quantum mechanics needed to be modified, but most other physicists resisted this conclusion. Giving up information conservation would have profound implications for quantum mechanics and would create other theoretical problems. After decades of debate, Hawking eventually conceded that information is probably conserved, though the mechanism remains unclear. The current leading idea is that information is somehow encoded in subtle correlations in the Hawking radiation. As particles escape, they carry away information about what fell in, but in a highly scrambled form that would be nearly impossible to decode. This requires quantum entanglement between the escaping radiation and the black hole's interior, creating subtle connections across the event horizon. The mathematics is complex and still being worked out. It involves string theory, holographic principles, and other advanced theoretical ideas. But the core insight is that black holes might not be as simple as they appear in classical general relativity. Their quantum properties might be far richer and more complex than we initially thought. As we near the end of this journey, let's zoom out and think about what black holes mean for the universe as a whole. They're not just exotic curiosities. They play crucial roles in cosmic evolution. Stellar mass black holes are the end states of massive stars, the final stage in a stellar life cycle that enriches the universe with heavy elements. Supermassive black holes regulate galaxy growth, influencing when and where stars form, shaping the distribution of matter on the largest scales. Black hole mergers, detectable through gravitational waves, teach us about the population of these objects, about how binary systems evolve, about the strong field behavior of gravity, and, theoretically, black holes are laboratories for understanding the deepest laws of physics, places where quantum mechanics and general relativity collide, where our theories are pushed to their limits. Every black hole is a natural experiment in extreme physics, conducting itself without any input from us, following the laws of nature to their logical conclusions. So what have we learned from this journey? We've learned that falling into a black hole, while ultimately fatal, isn't the instantaneous catastrophe you might imagine. For a supermassive black hole, you could cross the event horizon alive and aware, experiencing one of the most profound transitions in all of physics. We've learned that time and space behave in ways that defy everyday intuition. Time flows at different rates in different places. Space and time can exchange roles. What's possible and what's inevitable depend on where you are in curved spacetime. We've learned that tidal forces, the gentle phenomenon that creates ocean tides on Earth, becomes a powerful destructive force near compact, massive objects, capable of tearing apart anything that gets too close. We've learned that different observers can have profoundly different experiences of the same events, that there's no universal now, that reality is more flexible and observer-dependent than we might have thought, and we've learned that there are still deep mysteries. What happens at the singularity? Is information truly conserved? How do quantum mechanics and gravity work together at the most fundamental level? These questions remain open, waiting for future discoveries, future theories, future insights. As this journey comes to a close, I want to emphasize something important. Everything we've described is based on our current best understanding of physics. General relativity, which describes gravity and space-time. Quantum mechanics, which describes the behavior of matter and energy at small scales. Observations of real black holes through telescopes and gravitational wave detectors. But our understanding is incomplete. We don't have a complete theory of quantum gravity. We can't directly observe what happens inside an event horizon. Much of what we've described is based on mathematical extrapolation, on taking our theories to their logical extremes. It's possible, even likely, that reality is stranger and more subtle than our current theories suggest. There might be new physics near the singularity. There might be quantum corrections to the event horizon. There might be phenomena we haven't imagined yet. Science is always provisional, always subject to revision as we learn more. But what we've described represents our honest, best attempt to understand what would happen, based on everything we know, and that's both humbling and exciting. Humbling because it reminds us how much we still don't know. Exciting because it means there are still profound discoveries waiting to be made. The black holes are out there, Right now, scattered throughout the universe, stellar mass ones, formed from collapsed stars drifting silently through galaxies, supermassive ones, sitting at the centers of galaxies, including our own Milky Way, shaping the evolution of cosmic structure, pairs of black holes spiraling toward each other, sending gravitational waves rippling across SPAC-ETIME, all of them following the laws of physics, warping space and time, existing at the boundary of what we can understand. And we're here, on our small planet, studying them from a safe distance, using mathematics and observation to understand what we can never directly experience. It's one of the triumphs of human curiosity and ingenuity that we can study these objects at all, that we can send spacecraft to observe them from nearby, that we can detect the subtle ripples they create in space-time, that we can even image their event horizons. We've come a long way from wondering what they are to understanding them in profound detail, but there's still further to go, still deeper mysteries to unravel, still more to learn. Our imagined journey tonight was about experiencing the fall into a black hole, about understanding what would happen step by step, but it was also about something larger, about pushing our understanding to the limits, about exploring the most extreme phenomena nature has created, about confronting the strangeness of reality itself. Black holes are places where the universe reveals aspects of itself that we'd never encounter in everyday life. Time dilation, space-time curvature, event horizons, singularities, they're natural laboratories, showing us what happens when gravity becomes as strong as it can possibly be. And by studying them, by imagining what it would be like to approach them, to fall into them, we learn not just about black holes, but about the fundamental nature of space. Time, matter, and energy. We learn what reality is really like, beneath the familiar surface of our everyday experience. So our journey ends here, at the edge of understanding. Having fallen through the event horizon and contemplated the approach to the singularity, you're safe, of course. You've been safe the whole time, here on Earth, comfortable and secure. This was always an imaginary journey, a thought experiment guided by real physics, but hopefully it's given you a sense of what these extraordinary objects are really like. Not the Hollywood version, not the sensationalized nightmare, but the real thing, as strange and beautiful as anything in nature. Thank you for taking this journey, for being curious enough to wonder what would happen, to explore the question deeply and carefully. The universe is full of wonders, and black holes are among the most wonderful of all. They're out there right now, doing what they do, warping space-time, pulling matter into the ultimate point of no return, existing at the boundary between the known and the unknown. And we'll keep studying them, keep learning from them, keep pushing our understanding further. But for now, let it all settle. Let the strangeness of it wash over you and then fade into the background. You've traveled far tonight, to the event horizon and beyond, to the limits of physics and the edge of the unknown. Now it's time to rest. Let your breathing slow. Feel the solid ground beneath you, the ordinary, comfortable space around you. You're here. You're safe. The black holes are far away, and you're home. Close your eyes. Let your muscles relax completely. Let your mind grow quiet and still. The journey is over. Sleep is waiting. And tomorrow, if you wish, there will be other journeys, other questions to explore, other wonders to discover. But tonight, just rest. The universe will keep turning. The black holes will keep spinning. And you'll be here, safe and sound, dreaming peacefully. Good night.